All right, and let's begin today's summit with our keynote speech, Enabling a Low-Carbon Compute Future by Mr. Russell Tham, Joint Head Enterprise Development Group Singapore Head, Strategic Development Temasek. Russell was previously President of New Enterprises and Ventures at ST Engineering and President at Applied Materials. He's going to touch on challenges companies may face due to climate change and his thoughts on how to enable a smarter, greener, and more sustainable computing future for everyone. So ladies and gentlemen, shall we put our hands together to invite our first speakers of today, the keynote speech, Mr. Russell Tham, please.
Good morning, Minister of State Alvin Tan, SSIA Chairman Andrew Chong, and a dear friend, SSIA Executive Director Wee Sing, and fellow delegates. It's really great to be among many, many familiar faces and friends. But before I start, it's quite rare I come up and say something when the two preceding speakers say I have all the solutions to everything. So let me calibrate the expectations a bit. It's slightly below that, but I'll try my best. I think as both the speakers have mentioned earlier, semiconductors is and will continue to be at a foundational technology for digital, connected, and smarter world. Like the preceding two speakers also, pre-COVID was an era where we took semiconductors for granted. Post-COVID, obviously, no longer the case. We suddenly realized, not us, but the general public suddenly realized how critical and ubiquitous semiconductor is. This is a foundational technology that had a lot of practical uses. During COVID, if not for semiconductors, I'm quite sure you can't order your groceries online and have them delivered to your doorstep. I was walking up this morning, I nearly ended up at the wrong floor. I looked, token 2049. Crypto, NFTs. So we're one level below. So we are foundational technologies, no semi, no crypto. Okay. So until very recently, I think this is an industry that I think a famous New York Times columnist and Pulitzer Prize winner, I think Thomas Friedman, in his book, I think quite a seminal book in 2005, he wrote, "The World is Flat." I think some of you may have read that book. I read it as a kid, or a younger person, not a kid. It epitomizes globalization and rising prosperity. And in many ways, semiconductor was part of that journey, right? We lived in a world where it was flat and there were uninhibited trade flows across borders. Again, obviously, today, this industry occupies the center stage in terms of geopolitics. And many, many countries have now embarked on industrial policies that they were anemic to in the past, or kind of allergic to, and have embarked on this. I think US is one such country. Yeah. So no doubt, I think this is a very top of mind matter for many of you in this room. But in the meantime, we have a parallel and existential challenge. We talked about it earlier, right? Our climate crisis. If you frame it as a grand challenge, how would you pose this question? Can the industry transition to a low-carbon compute future? And as the video showed earlier, play an outsized role in solving this climate crisis. Now, to that end, let me give you three loose use cases that kind of give you a sense of the carbon footprint we are dealing with within the semiconductor industry and the broader ecosystem. First is the iPhone. Second, data centers. These are very pervasive and growing extremely rapidly. And then finally, the semiconductor manufacturing process. Now, when it comes to global warming, if you look at an iPhone or any smartphone, there's two components of carbon emission, loosely speaking. There are many ways to cut this, but I'm cutting it into two. How much emission you generate by making it through end-to-end. Then when you're using it, how much do you generate? And this ratio may vary, depends on the use case. But in the case of iPhone, here are the stats. Now, the approximate split between making the iPhone and then using the iPhone with some set of assumptions around a 4-year lifetime and a host of other, let's call it reasonable assumptions, 83% of the carbon emission is coming through the lifetime of this phone from making it, all the way from generating the silicon to reaching it to your doorstep. Now, 13% comes from using it. Okay, so that's give you a sense. Now, the total emission, in absolute terms, is 70 kilograms per iPhone through the lifetime of the phone. Now, you can go and burn a bit more carbon, use your math, how many iPhones and, per year, and you get the math. So these are not inconsequential emissions. So I think in some industries, we will call it embodied carbon. That means how much carbon you consume making it. So the building industry uses this terminology. Then operating carbon, when you're running your fab, how much you're generating, right? So our semiconductor value chain, especially the front end, are inherently quite energy intensive. I think all of us know this. I think we are grappling with high energy prices, and I'm sure it causes quite a bit of consternation among all of us here. But if you look at just TSMC alone, it uses more electricity than Taipei today, and it's also forecasted to exceed Sri Lanka's total energy consumption in the next few years, or probably towards the middle of the decade. Now, moving on to data centers. I think data centers intuitively, it's growing exponentially, right? It's driven by the amount of compute you need, the storage you need. All of us are depending on the cloud today, and the data we generate is quite exponential, I think. I guess all of you can attest to that. I think there's one more additional driver also, the proliferation of AI models, especially the transformer models. If you unpack the transformer model, it's very, very data compute intensive. So that is also another driver. So there are many drivers that will create significant growth in energy consumption for data centers. Now, one statistics I came across the other day is this, right? The data center energy consumption is expected to exceed Japan's 2020 energy requirements before the end of this decade. I repeat, data center energy consumption is expected to exceed Japan's 2020 energy consumption before the end of this decade. That's a lot of energy. And this is even after taking into account the fact that energy per unit operations or energy efficiency is improving 2x every 2 years. It's a rather remarkable statistics. Now, what can we do as an industry? I think this is widely discussed. There are broad areas we know what to do, but maybe let's talk about 3 areas. Now, first, and this is obviously a pain point today anyway, is the adoption of renewable energy. Yes, Singapore has its constraints, but we need, to the furthest extent possible, practically possible, drive renewable energy adoption. The good news is there is a tremendous investment in clean energy infrastructure and technologies. Last year, technology and renewable infrastructure related investments is north of $250 billion. That's a lot of investment and capital poured into building a renewable energy infrastructure globally. Now, the problem is, obviously, this is also an equally humongous task. The scale is ginormous, to say the least. And this will take time. So we have to march towards this, and we as an industry ought to think of innovative ways to push the boundaries, right? Of course, Russia's invasion of Ukraine has placed energy security as its clear first among equals within the energy trilemma of cost, security, and sustainability. But nevertheless, I think this is a speed bump. I think many countries have woken up to the fact that while they deal with energy security, which fundamentally also requires new investments, I think some of these new investments are going to be targeted or accelerated towards the renewable clean energy space. So you may see a speed bump, but in the midterm, I think we hold the view this energy transition, at least from a renewable energy perspective, will accelerate. So the industry can play its part, I think, by creating demand for clean energy. And I meant this in a more global context. Yeah. Demand drives investment. Investment drives scale. Scale drives costs lower or costs down. A dictum this industry is very well accustomed to. Now, secondly, the typical operating energy efficiency measures apply. I think we've talked about it in various forums. The rapid adoption of more efficient energy cooling techniques, lighting, smarter energy management systems will help. Very heartened to hear ST Microelectronics, I was about to say ST Engineering, has adopted district cooling. And I think that's a good start, right? I think here, Nike's slogan is quite relevant, just do it. In Singapore, of course, with some help from the government. The other area within this context, within this adoption thing is around what I call green semi-manufacturing. This is an area I think we could do with a lot more mind share. Yeah. Process improvement, alternative chemistries, they are a lot less energy intensive as you think through how to operationalize new chemistries, comprehensive abatement, areas certainly the industry can actively pursue. Developing various manufacturing strategies, process integration techniques, process recipes specifically, that inherently uses less energy while meeting, obviously, the myriad of specifications and process parameters that you guys always have to contend with, could be given high priority. Right? I think today, unless I have two data in the industry, that's not an equal weightage by which when we think of new process technologies. Now, third is something maybe slightly less shared about, discussed. Maybe this is where we are stuck in the value chain in Singapore. It's around how energy efficient is a compute architecture when we are using it. I use the iPhone example, 13%, but I think in data centers, the ratios are fairly reversed, if I'm not wrong. Yeah, this can be measured in energy consumed per unit of compute operations. Now, today's mainstream compute architecture, the von Neumann architecture, where we shuttle lots of data back and forth between memory and compute parts of the chip, is actually quite untenable, increasingly untenable. I distinctly remember maybe 5 years ago when I was still at Applied Materials, the CEO of NVIDIA, Jensen Huang, came and said, "Gentlemen, the amount of energy I consume actually at the compute part of the chip is less than 5%, or even, I think even less than that. The rest is around storing and shuttling memory around." All right, that's 5-6 years ago. So much of the energy is wasted when you move things around. It was also generating a lot of heat. And hence we have discussed all this, how do we cool the heat we generate from compute? And it's a bit of a vicious cycle. Also more recently, I was working on an investment case in this domain, next generation architecture. Someone recounted a story to me at a top semiconductor company. There was this internal joke, right? Half the chip design organization, the guys that design the IC and the whole 9 yards, is focused on turning on transistors to use them. He said, but the other half is focused on turning off the transistors. Why? Constrained by thermal budget and overall heat capacity of the chip. Right, so this is quite fundamental. It is illustrative that there is a limit by which our current architecture can process increasingly amount of data, especially in the AI-centric environment. Right? So the von Neumann architecture is a bit long in the tooth in my view, especially in an AI-centric world. So where does it lead us? If you look at the cutting edge of semiconductor chip design, there's a lot of emerging innovations coming forth in new architecture designs that will inherently be a lot more energy efficient. It doesn't mean it use no energy, it's just not possible, but vastly more efficient, right? So at Temasek, we've looked at quite a number of these, and I'll share a bit of this later on in the speech. Now, similarly, we are fundamentally based on a CMOS architecture. If you look at if you plot a curve, on the vertical axis, it's heat per area density. Horizontally is time. You go back 60, 70 years, you look at the BJ, I think the bipolar junction transistors, eventually you see a hockey stick where the energy density or heat density has reached a threshold that is no longer sustainable. Then came CMOS. The same curve peaked out 10, 12 years ago, I think. And that's why top semiconductor companies have to think of when to turn on and what to switch off. And people in the testing companies are designing capabilities to operate at a much higher temperature regime within their chip architecture. Now, what's the next curve that allows more compute power without so much heat inefficiencies or heat generation? So in that context, there are innovations emerging in the market where you have this intersection: materials innovation, chip design, and chip fabrication, right? Some call this beyond CMOS. I think it takes time, but we need to think about it. This multidisciplinary innovation could change our compute energy paradigm without sacrificing the performance that we all demand, right? For example, new material stacks that operate at vastly lower voltages in high-performance compute can be a significant reduction in terms of energy consumption when you do the same compute. So imagine if you have an SRAM technology that is buttoned next to the CPU that operates at millivolt voltage. Very different. Likewise, in the other end of the spectrum, in the EV space, electric vehicle space, next generation of high voltage powered ICs increases efficiency in the overall architecture of the battery design, the car design. And maybe not so known to many people, the amount of materials, wiring, and the whole 9 yards is also vastly reduced. Now, this is sustainability. You use less to produce the same outcome. So where does this roughly bring us, right? I think, carbon is really a cost. Andrew has talked about it, Minister has talked about it, and it has to be treated as such in the course of doing business. So now let me shift gears a bit. I want to share a bit of Temasek's journey in this, maybe slightly less semi, but I've kind of framed it in a more semi context. So at Temasek, we are fully committed on this journey. We want to play a catalytic role in enabling a sustainable future, and we are all in. We have committed to halving our portfolio emissions that we emitted in 2010 by 2030. And I use the word portfolio because bulk of the friends here are not from the investment industry. That means this includes SSIA, not SSI, right? The burn fuel carbon emissions. So portfolio is big. At the level of Temasek, internally, not an issue. But at the portfolio level, it's big. We have already priced carbon. We started 2 years ago. Today is $50. We think it'll be $70 in 3-4 years, and certainly $100 by end of this decade. We are putting in place long-term incentives for the staff in terms of carbon emission reduction targets. We are also investing at a much lower carbon intensity, as measured by how much carbon is emitted divided by your portfolio value. So how much carbon is emitted at the portfolio divided by your portfolio value. Okay, this is not exact science, but you do a lot of modeling. So if you look at our 10-year average and the last 2-year average, we have reduced this by a factor of 5 to 6. So we are going down this path. Now, that doesn't mean we sell everything that is potentially carbon emitting, right? So we also embark on a journey to help our large portfolio companies decarbonize. We're running pilot trials for Singapore Airlines in partnership with a few other players to trial sustainable aviation fuel. We're working very closely with Sembcorp, who is here, to decarbonize. So these are all very critical factors. So we do not just say, it's easy as an investment, I sell everything that is remotely carbon related. We even invested together with Brookfield. It's a huge infrastructure fund. They call it the Energy Transition Fund, helping infrastructure companies move from brown to green. So we are all in. Now, specifically, as a long-term global catalytic and long-term investor, we also invest in a lot of emerging and disruptive technologies. Technological innovations which go beyond marginal incremental improvements to the existing BAU. Technology innovations that are orthogonal to the existing order. Now let me cite 3 categories that we work on. And we do have a broader context, but in the interest of time, I thought keep it tight to 3 things. So first, clean energy value chain. Right, this is a huge endeavor, as you can imagine. We have invested in next generation PV technologies. Some are without silicon, sorry, because silicon inherently is also an energy intensive process because high temperature is required, right? We've invested in a bunch of hydrogen technology, electrolyzers, carriers that operate at different economics and different efficiencies. We've invested in advanced geothermal, extracting heat from the ground 5-6 kilometers down to generate electricity. We've invested in nuclear fusion. Nuclear fusion. If this comes true, I can safely say Singapore got a get out of jail card for all of you. And we're also thinking about fission, nuclear fission, because why? Energy security. We've also invested in utility scale batteries that doesn't require lithium. Lithium is not exactly a clean mineral from the extraction process, and it creates quite a bit of waste, but instead use fairly more common materials. So the 2 investments, one uses iron, one uses sodium. And both at a different end spectrum. One is ultra long duration technology, one is ultra cost effective, but not volumetrically efficient, but it's okay. We'll look at it. Now, second is building and infrastructure and transportation. Okay, when you build a fab, there's a lot of embodied carbon. Cement is 70%, steel is 8-9%. So these 2 are effectively also a significant portion of your carbon footprint. I think fabs aside, if you look at a more regular building, non-heavy industrial, heavy temperature, high temperature type industrial process, typically the lifetime of your building, the split is 60-50% embodied carbon. That means how much carbon you use to build the infrastructure, 40% comes from using it. So that's the ratio, but I think fabs obviously not this case. Yeah. So in that regards, we have invested in low carbon steel, low carbon cement, which I hope in due course as this technology mature, when we build up new fabs, we should use this. Little interesting fact, actually, if you read this sector, it's a lot of talk about green steel. And green steel got 2 parts, right? Making the steel and the step before steel, turning iron ore into high-grade iron, around 98% before you can put it into the furnaces to add in the impurities for steel. 90% of the carbon emission comes before you enter the steel furnace. Right? So how do you invest in that extraction and purification process to use orthogonal technology without heat, or much lower heat? Battery transportations, we've invested in a range of battery technologies for EV, anode-less, lithium. Now even looking at stuff that use sound wave to prevent what they call the first charge. There's a technical name for it, but essentially when you charge the battery for the first time, there's a significant drop. So how do you mitigate that? So we've done a lot of this stuff. We've done fuel cell stuff. Now third, next generation computing, I was alluding to it earlier. Material innovation, very important. Material innovations that can allow ultra low voltage memory or logic computing, I think could be a frontier that takes on a much larger role in helping us decarbonize our industry. I mentioned about AI earlier, right? Data flow architectures for AI training is really, really energy intensive. Today, these transformer models, you put it into the most advanced NVIDIA GPU, takes a few days and a few $1 million to go retrain your model. Then you push out the model into an inference site, right? So people are thinking through what is a better architecture to train your AI models, especially the big ones. So there are startups in that range. We have invested in that category. Now, when you've trained your model, you move it out into inference compute architecture. Today, it's also not that efficient. So a lot of stuff are being thought through there around what we call in-compute memory in the digital. People can make analog in-compute, but digital in-compute constructs for inference training is also, for inference models is also an area that I think quite critical. So in US, I spent a bit of time there. I must say the energy equation, the sustainability equation, when some of these folks are working on very advanced technologies, next generation compute architecture, is quite high in their mind share. Right? So I think I want to put this ahead to you guys so you know what wave is coming in the next 5-10 years. And oh, by the way, we have also invested in quantum computing. Now, one part of quantum computing is quite energy intensive. The mainstream, I think you read Straits Times, all talk about superconducting. Environment that requires ultra low temperature, millikelvin, 0 Kelvin, or very close to that. So we are investing in higher temperature computing technologies, right? So that is also forth of mind. If you want to have quantum computing technologies that require millikelvins to cool the whole system, you have lots of energy, right? So we're looking at cold atom quantum computing. We're looking at photonic-based computing, quantum computing, which operates at non-millikelvin temperatures. Okay, I'm deciding whether I have a 7-second break because I want to make a pitch. So I'll take the 7 seconds. By the way, I'm hiring. Talking about talent, I'm looking for purposeful workaholics who have a passion for first principles deep tech investing, which are enabled by emerging STEM innovation. So please look for me later if you are interested. Workaholics, very important. Second, first principles deep tech investment, your ability to unpack the technology on a first principle basis, understand the technology entitlement, understand the de-risking pathway, the unit economics, and you're intellectually very curious, then look for me. And about 100 hours a week, that's about it. Now, in closing, semiconductors have changed the way society lives. I think all of us know that, and I think really for better and irrevocably. Like Andrew and Minister said, we are well known for our velocity, our innovation. I must say, I'll add our audacity too, and also our talent pool. Coming from the semiconductors, I thought we have a lot of bright people. I think the other industry that potentially parallels it is also the investment industry. It attracts that kind of people for maybe slightly different reasons, but also a lot of talent. Right? Now, can this mighty industry, iconic industry, take on a concurrent grand challenge? We have been in a single pursuit of just driving semiconductor advancements. Right? Now, there is a concurrent challenge. We talked about it. Right? How can we play an outsized role in solving this climate change? Now, this year, I was in a conference in Sonoma on semiconductors, and I thought this was very interesting statistics. 11%, just this, I think the year is not out yet. The year is not out yet, but 11% of the weather stations in US, since the time of its recording, recorded highest temperatures ever. 11% of the weather stations in US, since all these stations have been recorded highest ever temperatures. Right. I think every day we read Straits Times, you can see extreme weather events. I think now it's in Philippines, in Florida. Now, if you go back 10 years ago, sorry, Minister, I got to a minor banter at the Singapore government. 10 years ago, there was I remember reading in the press, there's a rare flash flood in the intersection of Orchard Road and Scotts Road. So what piqued my interest, because the press was reporting, I said, what's the big deal, right? But, it was a rare event then, and, we had a creative way of labeling it. We call it bonding. Right, so I was laughing, okay. But, 10 years fast forward, in all seriousness, Singapore has a full-blown coastal protection strategy, I think well-baked, based on what I can tell, that spans a few generations, right? And also recently, obviously Temasek is part of this journey to support a net zero commitment by 2050 or around 2050. So at Temasek, our purpose is intergenerational. And it's encapsulated in 4 words on it. Right? So every generation prospers. 4 words. So every generation prospers. We, all of us in this room, your children, your grandchildren, your great-grandchildren, will have a better chance if we solve this climate crisis together. Right? I believe the semiconductor industry is perfectly capable of one more great act, or at least a few more great acts, and help play an outsized role in this. So with that, I want to wish all of you a fantastic conference. And I always end off with closing in this way because I'm a Star Trek fan. Live long and prosper. Thank you.
Thank you, Mr. Russell. We do wish you have more time for you. We have so many questions coming in. Okay, perhaps we have this question. You mentioned in your speech that Temasek actively invests in emerging and disruptive technologies. What startups or new technologies has Temasek looked at?
We looked at okay, first let me clarify, because in my side conversation with Andrew and Minister, Temasek is not part of government. That I don't express a government view, right? So just let me clarify that in case energy question comes up. Okay, we invest, if you look at the sovereign wealth rankings, despite our best effort to not label ourselves as sovereign wealth ranking, my fellow friends in the government also call us sovereign wealth ranking, so it's okay. But we are the top investor in early stage technologies. And by that, it includes a lot of energy investments. One of the reasons I came on board for Temasek is to really accelerate our ability to deploy capital at the very early stage of deep technologies, be it in energy transition, be it in next generation computing. I think these two are more relevant here. Of course, we do all the other stuff, food technology, sustainability related like plastics, bioplastics, alternative protein, the whole 9 yards. But specifically, what we are looking for, orthogonal disruptive technology that can disrupt existing order that shifts the paradigm of performance. And how do you understand it so early? I mentioned earlier, right? You need to understand the technology entitlement. What is it capable of if it's fully de-risked at what unit economics is critical? Now then, this all take time. You fast forward it to your best guess what the market, the customer, and the competition will look like. And you say that's kind of how you capture the value, right? Now in between is the team. Your R&D team, your product architecture, your business model, your go-to-market. And it's all a function of how differentiated you are to a future existing order. The better you are, the better you can extract value. So we've done a lot. I think we actually cap ourselves at 6% of our portfolio today in the context of not deploying more than 6% of our $400 billion in early stage technology. So that's maybe a general answer.
Sure, thank you. Because of the time, we are unable to take more questions. All right, so that will be one question for you, Mr. Russell. Okay, thank you. Okay, thank you so much, Mr. Russell. Thank you for your time. A pleasure to meet you in person. Pleasure. Thank you for your sharing.